will drive an increase in atmospheric evaporative demand, and therefore an increase in aridity and in the frequency of drought, at least in the regions where there is no large increase in precipitation. And finally, global warming can also alter the atmospheric circulation, for instance, lead to a narrowing and strengthening of the tropical rain belt or to a poleward shift in the storm tracks. So moving now to the observed changes. One first key finding is a stronger assessment that the emissions of anthropogenic greenhouse gases and aerosols have been associated with distinct fingerprints of temperature, precipitation, and aridity across the 20th century. So the ongoing global warming, greenhouse gases induced warming on the left is associated with contrasted changes in precipitation and with an overall increase in aridity in many regions. While on the right, we see that the time evolving emissions of aerosols have been associated with, mostly from the northern hemisphere, have been associated with an interhemispheric temperature response, a southward shift of the tropical rain belt, and have counteracted the aridity response to greenhouse gases emissions in the northern mid-latitudes. Beyond, to further support the importance, of anthropogenic aerosols, we see here the average summer precipitation anomalies, so over land in the northern hemisphere. And we show the observation in black showing a decline in precipitation from the 1950s to the 1980s, followed by a recent recovery, which is also typical of what has been observed, for instance, over the Sahel, with dramatic droughts in the early 80s, for instance. And we see that most CMIP6 models, although they underestimate this long-term evolution, do capture this evolution when they are driven by all radiative forcing, and their ensemble mean results are here shown as a red solid line. And this long-term evolution is clearly the combination of a long-term increase in precipitation due to increasing concentration of greenhouse gases here in pink, and a vanishing opposite response to anthropogenic aerosols in blue. Beyond mean precipitation, the formal attribution studies have been also applied to heavy precipitation events and have led to the conclusion that the global warming due to anthropogenic climate change has already led to an increase in both the frequency and intensity of these events since the 50s. At least in most of the IR6 region, where we have enough data to make such an assessment possible, as shown in grid in this figure. And also, circulation changes may alter where and how often these more severe, more intense agroclimatic events will occur. In addition, trends in terrestrial water storage observed from space, for instance, using recent observation from the GRACE missions since the early 21st century, clearly show that in some regions, water restriction for irrigation has had a dramatic impact on water resources, as for instance, around the Aral Sea, which was one of the fourth greatest lake in the 50s and has strongly shrunk over recent decades. Moving now to the projected water cycle changes, a first key result is the fact that most water cycle changes will become larger in direct relation to increasing global warming levels, not surprisingly, and in line with what has been showed earlier by the special report on global warming at 1.5 degrees, for instance. This is true for annual mean precipitation, as shown here for 3 global warming levels at 1.5, 2, and 4 degrees respectively. But this is also true for most wet and dry extremes, as will be explained later by Sonia. Beyond changes in precipitation, all scenarios, including the intermediate SSP2 scenarios shown here, based on CMIP6 models, show a relative increase in land surface evapotranspiration over most land areas and a decrease in soil moisture in many land areas, while relative changes in annual mean runoff show similar but exacerbated patterns compared to precipitation changes. If we focus now on projected changes in seasonal monsoon rainfall, we see that CEMIP6 models, most of them project an increase in global monsoon precipitation, particularly over South and Southeast Asia, but also East Asia and West Africa, apart from the far West Sahel. And we also have assessed some changes in monsoon seasonality with a delayed onset over the Americas and West Africa and a delayed retreat over West Africa. Finally, if we plot here changes in annual mean precipitable water, total precipitable water, in black, mean precipitation in blue, or mean runoff in brown, as a function of global warming levels, and this is here average for tropical land area, we again clearly see an overall intensification of the water cycle with increasing changes for increasing global warming levels. But we see that, for instance, the mean precipitation increased much less than the mean precipitable water, that is the mean atmospheric water column, which itself increases at a rate that is closer to the Clausius-Clapeyron rate of 7% per degree Celsius of atmospheric warming. And we also see that the year-to-year variability shown in dashed line of the water fluxes increase more than changes in mean fluxes for both precipitation and runoff, highlighting that there will be more volatile water resources in the future, a stronger volatility of future water resources. So all those findings are quite robust, are based on multiple evidence and multiple generations of CEMIP models, but there are still limits for projecting water cycle changes whose quantitative assessment remains uncertain and cannot exclude the potential for abrupt change. For instance, if we mix all CEMIP6 models and all SSP scenarios, and we show here total uncertainties in the annual mean precipitation response, we see that the total uncertainty can be arise from three contributions whose relative importance depend on the selected time horizon. For instance, in the top panels, in the near term, uncertainties are dominated by both internal variability and model response uncertainty, while precipitation changes are not much sensitive to the emission scenario, which highlights the need for urgent adaptation and careful adaptation. If we look now to the mid to long term, we see that the role of internal variability vanishes, but that uncertainties are still dominated by the model response, highlighting again that both mitigation and adaptation strategies need to consider the full or at least the likely range of model outcomes. This finding is the same conclusion can be drawn from this panel, showing the annual mean changes in runoff average over large-scale river basins, 9 river basins, with most basins showing a wide range of 90% confidence interval in their response, and some basins even suggesting that the ensemble mean force response is not a fully linear function of global warming, of increasing global warming on the x-axis. Such non-linearities can arise from land surface feedbacks and related tipping points, but it can also arise from changes in oceanic circulation. And for instance, here, as illustrated by the annual mean precipitation response, which has arisen in the past or could arise in the future from a collapse in the Atlantic meridional overturning circulation. So the IR6 report states that there is only medium confidence that the hammock will collapse or will not collapse, before the end of the 21st century. But should it collapse, it is very likely that there would be abrupt changes in the water cycle, especially in the tropics. So some key conclusions and the implication for adaptation and mitigation. I won't repeat all the key findings, maybe just add that over specific regions, we will have also some decrease in mountain glaciers and snow cover duration, with strong implication for runoff and river discharge. We will have some intensification of tropical cyclones and extratropical storms, with increased related precipitation intensities, and an increased proportion of tropical cyclones of the highest category, the most powerful ones, with related increase in river flows. And over the 21st century, again and beyond, we cannot exclude the possibility of abrupt and irreversible regional change in the water cycle. So what about the implications? We can say that without further adaptation, existing water-related risk will be exacerbated with further global warming, that careful adaptation responses are needed, not only to avoid the most adverse water cycle consequences of global warming, but also to avoid maladaptation and the lack of co-benefits for mitigation. And finally, that land-based mitigation option can have considerable water footprint and probably also need to be managed carefully. So in summary, we can say that water is an issue for all of us and for all dimensions of our climate change policies. Thanks for your attention.
Thank you. Thank you so much, Harvey. That was a fantastic presentation, providing very good summarized outputs from the assessment, Working Group 1 assessment, and the implications you drew for Working Group 2 and Working Group 3 were also spot on. I mean, a lot of our findings in Working Group 2, which is due to be released in February, March next year, actually also echo your findings. With that, I would now like to pass on to our next speaker, which is Dr. Sonia Senaviratne. She is in the Water Pavilion right now and will join us live from Glasgow. She's a professor of climate sciences at the ETH Zurich and is a coordinating lead author of the Extreme Cycle. She will talk about the water-related extreme findings from her chapter. Over to you, Sonia.
Do you hear me? Yeah? Okay, great. Thanks a lot. It's a pleasure to make this presentation. I would like to thank the organizers for the invitation. And I will present the main... I think people here don't hear, but... Okay. Yes, so I will present the evidence on changes in water cycle extremes in the IPCC AR6 report. Next. So I just want to say that the work I'm going to present is work from the Chapter 11 team. We had a team of 16 authors, and we coordinated this chapter together with Xubing Zhang from Environment Canada. Next, please. So we already have large evidence of observed changes in extremes. The evidence of observed change in extremes has strengthened, in particular for extremes related to the water cycle. This is, for instance, related to precipitation extremes, droughts, tropical cyclones, and compound extremes, which also include dry and hot events, as well as fire weather. You see here pictures of the different extremes that we have been assessing in the report, and as you can see, many of them are related to the water cycle. Next, please. Next. So human-induced climate change is already affecting many weather and climate extremes in every region across the globe. I think this is one of the main conclusions of the report, that we see that no region is spared from climate change. Every region is affected in some way by changes in extremes, including water cycle extremes. Next. So I'm showing here a few examples of events of which we know that they have been made more probable due to human-induced climate change. For instance, flooding in Bangladesh in 2017, the fire and heat wave in Australia in 2019 to 2020, also the high heat wave in Siberia, which was also again associated with fire. And then this year, of course, we had a large range of events, including fires in Canada, then the flooding in Western Europe, which was associated with very heavy precipitation, and also high drought in Mediterranean. Many of those changes are related to water cycle. So for instance, this includes these concurrent heat waves and droughts. Here you have several examples, which are then also leading to more frequent fires. So when you have both dry and hot conditions, you have more probability of fires. On the other hand, you also have an increase in heavy precipitation, which increases the probability of floods. Next, please. So I'm showing a picture from different changes in extremes across the world. Hervé has also shown this picture for heavy precipitation. I wanted to start with temperature extremes because they are related also to some water cycle extremes because they amplify a drought. And as you can see, in all regions, almost all regions of the world, we see an increase in hot extremes. Next slide, please. For heavy precipitation, in most of the regions with observations, we also find an increase in heavy precipitation. Next slide, please. We also have several regions where we find that there is an increase in droughts, in particular droughts associated with drier soils, which have impact to agriculture and ecosystems. So you see that there is a range of regions where we have identified signals for increase in drought, and this is substantially more than the last report of IPCC. Next slide, please. I also wanted to mention some other type of extremes, for instance, tropical cyclones, which are also associated with heavy precipitation. So event attribution studies and physical understanding indicate that human-induced climate change increase heavy precipitation associated with tropical cyclone, and also that it is likely that the global proportion of major tropical cyclone occurrences has increased over the last 4 decades. Next slide, please. Human influence has likely increased the chance of compound extreme events since the 1950s. So we have an increased occurrence of concurrent heat waves and droughts on global scale. We have also an increase in fire weather in some regions of all inhabited continents, and compound flooding has increased in some locations. Next slide, please. So now we'll say a few words about projected changes in extremes as function of global warming, also focusing on water cycle extremes. So many changes in frequency and intensity of climate extremes become larger with increasing global warming. And I've listed here a few examples. This includes hot extremes, marine heat waves, heavy precipitation, agricultural and ecological droughts in some regions, and the proportion of intense tropical cyclones. As highlighted here, of course, we have those changes both in the very wet extremes and dry extremes increasing. Next slide. Next. And there is already much higher risk at 2 degrees compared to 1.5 degrees, as well as at 1.5 degrees compared to now. So now this slide, you're seeing how the change in the frequency of heavy precipitation is changing as function of global warming. You see that an event that without human-induced climate change would have happened once every 10 years is happening now about 1.3 times every 10 years. That means an increase of about 30%. At 1.5 degrees, the increase would be by 50%, and at 2 degrees would have an increase of 70%. So those events would happen almost every 2 years out of 10 years. Next, please. Next. You're seeing here also the change in intensity of extremes. In general, we see an increase of about 7% per degree of global warming associated with the Clausius-Clapeyron relationship. And so this means that we have a very clear signal in terms of increasing intensity of heavy precipitation events. Next, please. For droughts, it's a similar picture, but in this case, we're only looking at regions which are drying, so it's only part of the land area. For heavy precipitation, the statistics were for all of the land area. For the drying regions, you see that we have a range of regions where we find that there is an increase in droughts at 2 degrees of global warming. And again, there we have an increase both in the frequency of those events and in the intensity of these events with increasing global warming. Next slide. I want to say a few words about compound events. I think that's a really important point, and that's actually a new topic that was addressed in the report. What we are meaning by compound events is actually the concurrence of different extremes in the same location, or different extremes in different location at the same time, which are leading to joint impacts. So with further global warming, we find that every region is projected to increasingly experience multiple changes in climate impact drivers, including extremes, and that many regions are projected to experience an increase in the probability of compound events with higher global warming. This includes concurrent heat waves and droughts, which are likely to become more frequent, and also a further increase in fires and compound flooding. Next, please. Another really concerning point is that we have an increase in the concurrence of extremes at different locations, and this can lead to large impacts. So we can have concurrent extremes at multiple locations, including, for instance, crop-producing areas at 2 degrees and above compared to 1.5 degrees. This can affect, for instance, food security. Next slide, please. I just wanted to say a few words about what would be needed if we want to limit global warming to 1.5 degrees. We have seen that compared to 2 degrees, this will make a very large difference. And these are data from the 1.5 degree report. The scenarios that will be consistent with 1.5 degree stabilization are shown in blue. This requires an immediate reduction of CO2 emissions on a global scale by at least 50% until 2030. And to reach net zero CO2 emission at the latest in 2040 for 60% probability of limiting global warming to 1.5 degree, or 2050 for 50% probability. Next slide. So I'll come to the conclusions. Evidence on change in climate extremes, in particular for water cycle extremes, has strengthened in the past decade. We find that no region is spared from changes in extremes, and that threats from extremes are multiplying with increasing global warming. In a warmer world, water cycle extremes such as heavy precipitation, pluvial floods, or droughts are amplified in many regions. And limiting global warming to 1.5 degrees avoids numerous further increase in water cycle extremes compared to 2 degrees and above. We find also that compound events are an important factor of risk above 1.5 degrees, for instance, for fire risk, but also impact on food security. So my conclusion would be we should do all we can to limit global warming to 1.5 degrees and avoid overshoot. Even a world at 1.5 degrees is not safe. We have seen this now, even at 1.1 degree or 1.2 degree, we are having impacts. But it's the best option we have to limit global warming to 1.5. Thank you very much.
Thank you so much, Sonia, for an excellent talk. And the message is very clear that a large section of humanity are already experiencing climate change through water extremes like floods and droughts, and urgent action is needed to keep temperatures within 1.5 degree, something that the G2 leaders apparently agreed also yesterday. Let's see how that turns into action. With that, let me now turn my attention to two of our very eminent panelists. One of them is present in Glasgow in person, and another is joining us online. First, I'll go to Dr. Roxy Matthew, who is joining us online from India. And Roxy is a climate scientist at the Indian Institute of Tropical Meteorology, and he is the chair of the Indian Ocean Regional Panel. And he was a lead author for another IPCC report, the Special Report on Oceans and Cryosphere. To you, Roxy, my question is, I know you have been following these reports and contributed to them. Tell us your key takeaways from the report, especially the Working Group 1 Physical Science report, and situate these findings for us in the context of South Asia, which is likely to be one of the hotspots of climate change. And how can South Asia tackle climate change? Over to you, Roxy.
Thanks, Aditi. Hi, all. Thanks for attending the Water Pavilion at COP26. And thanks to Hervé and Sonia for giving a global overview on the changing climate and how the water cycle is changing. And here, I will give a perspective from the tropics, particularly in terms of South Asia and how the Indian Ocean region is faring. And one of the salient points that has come out from the recent sixth assessment report of the IPCC is that some of the changes are irreversible in terms of human timescales. That is about in centuries, centennial timescales, or even a millennium. And that is because the carbon dioxide lifespan is quite long in terms of centuries, and the ocean absorption is slow. And this also has huge implications for the tropics, which is linked to this heat absorption. In fact, about 93% of the additional heat from global warming is absorbed by the oceans. And the largest change is observed in the Indian Ocean. And whether it is sea surface temperature or the cumulative ocean heat absorbed in the last several decades, the largest change is in the Indian Ocean, and it's the fastest warming ocean. And this has implications on the water cycle in the Indian Ocean or the South Asian region, for example, the monsoons. And though the IPCC report hasn't mentioned that the changes in the monsoon are irreversible, considering that the changes, the underlying background changes in the ocean are long-term, the changes that we see in terms of the floods, droughts, and all could be irreversible as well for a long time. And now, and the second thing is that I would like to refer to what Sonia and briefly Hervé also presented in terms of the drastic changes in the future. And some of these changes for the Indian Ocean and South Asian region are already here. We don't have to wait for 1.5 or 2 degrees Celsius. We already see a 50% rise in the number of cyclones, and also there is an increase in its intensity and the duration of cyclones, especially on the Arabian Sea side in the Indian Ocean. And there is a threefold rise in extreme rainfall events and intensifying droughts. Now, that connects to our changes in water cycle, because if you look at all of South Asia, it's heavily dependent on how the water is spread out. In terms of the monsoon, we are already having changes in water in terms of floods, droughts, or cyclones. So water stress could permeate into agriculture, the food sector, and the energy sectors too. Now, another factor I would like to point out is that right now, we do not have the risk mapping or climate action to deal with the current state of extremes. And with 1.5 and 2 degrees Celsius, this is going, we know that this water stress is going to intensify further. And particularly, we do not know about the compound events that Sonia was talking about. For example, in the during the recent cyclones that we had the storm surges from the cyclones interacting with the heavy rains and the sea level rise, resulting in compound floods or floods that are much higher than the usual level. And this means that the flood levels are going up year by year, decade by decade. So curbing emissions are critical. And while it is important that cumulative carbon emissions are considered and all, it's also important that we all move towards the common goal. We cannot keep on negotiating and debating. That time is over for South Asia, because that is one of the most vulnerable regions. And South Asian region, including India, can lead innovation to mitigate and adapt to climate change. That's what I think, particularly by investing in efficient energy and being a global leader, particularly in South Asia. We have already made a strong leap in terms of NDCs, but we don't know how much of offsetting we are done in terms of fossil fuel emissions. That is one place where we are to work on. And hopefully innovation and technology is one way for a quick transition into clean energy. And there is hope, because among the few countries that brought out COVID vaccines at a first place, India is one among them. So we have the technology and people to work on from this region. And so my concluding message is that along with innovation and transition to renewable energy resources, adaptation measures should also be considered, considering the fact that the drastic changes that we have been expecting in the future are already here. Thank you, Aditi.
Thank you so much, Roxy. I think those were all excellent points. Now that makes me move to our final panelist, which is Dr. Valerie MassoDelmore. She is present in Glasgow and is at the Water Pavilion. If the cameras can zoom at her. I don't see her on my screen yet.
Can you hear me, Aditi?
Hi. Yes, I can hear you, Valerie. Yes, wonderful to see you, Valerie, there.
Nice to see you.
Yes, and thank you for accepting our invitation. So Valerie is a climate scientist working at the Paris CECLI, France, and she is the co-chair of the IPCC Working Group 1. In her role, she has co-supervised 3 IPCC special reports in 2018-19 and in the recent 2021 Physical Science Basis report. So Valerie, you have supervised the writing of these reports, so you have deeper insights into this than many of us present here today. So tell us your top 3 takeaways and also tell us what kind of scientific and policy advances that will be needed for us to keep within the 1.5 degree. That seems to be the absolutely necessary goal now. How do we keep within 1.5 degrees? So over to you, Valerie.
Thank you very much, Aditi. And I really like that here in Glasgow, there are 3 pavilions next to the other. The science pavilion involving IPCC, the cryosphere, frozen water pavilion, and the water pavilion. And as you have stressed, there are strong interplays between warming, water availability, water stress, and water management responses. I would like to flag 3 aspects, focusing on the Working Group 1 report. One, for me, striking advance is by combining multiple lines of evidence, the ability to narrow the range of the climate warming response to our greenhouse gas perturbation. It's a metric called climate sensitivity, and it's really striking that compared to our past assessment, we've narrowed the range of that response by about 50%. And this is the outcome of basic climate research, and in particular, progress in understanding crowd feedbacks. So that's a major advance, but at the same time, there's much more to be done. In particular, progress in understanding changes in clouds and convections, which could lead to major advances in further constraining future climate change, with major implications for the regional water cycle characteristics. The second part of all these reports is our clearer understanding of why every increment of warming matters, with multiple regional characteristics, trends, extremes, monsoon changes, values above tolerance thresholds that directly scale to the level of global warming. So as you have seen, I think a major conclusion from our report is the understanding of how the water cycle intensifies with every increment of warming, which in fact increases the adaptation challenges, because it means you have to adjust not just to trends, extremes, but also precipitation that becomes more variable from season to season and from event to event. You have seen the presentations flagging the better understanding of the role of greenhouse gases and aerosols, in particular on monsoons, but we still have a number of gaps regarding, for instance, in Asia, the onset or retreat of monsoons, and that requires further work in terms of physical climate science to inform adaptation strategies. You have seen from Sonia's presentation how we have a better understanding of already human influence affecting heavy rainfall events or droughts, but you have seen on the maps that we still have gaps in terms of availability of highly resolved meteorological hydrological records, or gaps in terms of available attribution studies, especially in the developing world. So I like to flag what we have achieved, as well as remaining knowledge gaps, to show how progress can be achieved to better inform adaptation strategies. Roxy has stressed the slow component response to human influence today. So there are changes that will not be avoidable. The response of glaciers will occur over decades, affecting streams flows, the response of the ocean over hundreds of years, ice sheets, thousands of years. What we show is that every increment of warming matters in slowing the rise of sea level, which gives more time for coastal adaptation regarding changes in erosion, coastal flooding, as well as salinization, which is important for water resources on coasts.
much of adaptation taking place today is still looking backwards, looking at what has been experienced. And I think a strong message from our Working Group 1 report is that we provide a wealth of information on what to expect. And I think a key point is for everyone involved in water management, in water-related decision-making, the use of climate services to better inform decisions made now by what to expect in the future, so looking forward so as to enhance resilience. Aditi, Sonia, Hervé, Roxy, you have all flagged the importance of the level of global warming. So our report shows that if emissions of greenhouse gases stay close to today's levels, just a few more decades, we'll overcome a level of warming of 1.5 degrees within 20 years and 2 degrees by 2050. So what really matters, because every ton of CO2 added in the atmosphere will imply more warming, is reducing CO2 emissions as fast as possible. And in the coming years, decades, because as long as our emissions are not at net zero globally, climate will continue to drift with more implications for changes in the water cycle. The report shows that for warming of more than 2 degrees, natural sinks, the ocean, the land, might be less effective at storing a large part of our emissions. And that's also an interplay with the water cycle, because plants facing water stress and heat stress will lose their ability to store carbon. That's another dimension of the interplay between climate change, natural sinks, nature-based solutions, and changes in the regional water cycle. And the last point we stress in the report is the possibility to have multiple benefits. By reducing emissions of pollution particles, it can improve air quality, but it will affect the water cycle as well. By reducing methane emissions, you can maximize benefits for air quality because it's linked to near surface ozone. And because by reducing quickly methane emissions, you can compensate for losing the cooling effect of pollution particles. So this is really a novel dimension of our 2021 report. And there's an intersection with water management because solutions exist related to waste water treatment that can help reduce methane emissions fast. This is what I wanted to share regarding the interplay between our last Working Group 1 report and water management challenges. Thank you.
Thank you so much, Valerie. I think those were, again, incredibly important points in terms of the need to adapt based on what will happen in the future, especially when we are not even sure if the current adaptation is being effective in reducing any of the much of the climate risk. So it's even more important to craft a future adaptation appropriately, and of course, the absolute importance of reducing emissions here and now. With that, we are almost out of time. So I would like to convey thanks to Hervé, Sonia, Roxy, and Valerie, and pass on to Dr. Mark Smith, who is the Director General of the International Water Management Institute. Over to you, Mark, for your key takeaways and concluding remarks. Thank you, everyone.
Thank you so much, Aditi. And a big thanks to our speakers and panelists, Hervé, Sonia, Roxy, Valerie. What you have done is laid out a cornerstone for the program in the Water Pavilion to come. What you've done in this session is given the very basis, the very starting point for the dialogue that is to come over the next 10 days and 2 weeks at the Water Pavilion. So, my reflections, a critical message as people take part in the coming sessions. You know, in the water community, we often say climate is water. And so why do we say this? And Hervé gave a very clear explanation that we say this because of physics. It's not because it's a sector issue, it's because of physics. And this physics drives the intensification of the water cycle, which is driving increased frequency and intensity of climate extremes that are becoming larger and will become larger as global warming increases. So water risks are therefore increasing. And this is happening in combination with higher uncertainty about extreme events. So it's a very difficult puzzle for water managers to contemplate. Water managers, indeed, Valerie, who are used to looking back, and now we need to be looking forward into the future with a different set of tools. So how do we do that? So it's incumbent upon us as we go forward, of course, to try and lower these risks, to manage these risks and reduce exposure to the water risks that climate change is unleashing. And this means, yes, as you've said, every increment of warming matters, therefore. We have to target for the purposes also of water management, stabilizing at 1.5 degrees C. So therefore, reducing emissions as fast as possible is water management. Combined alongside that, of course, there's a need for urgent adaptation. Adaptation must look forward, as Valerie said. We must adapt with care. We must ensure that there are co-benefits for mitigation as we undertake adaptation, that we avoid maladaptation. As we move forward into adaptation, we need to look also for how do we do so alongside the energy transition? How do we do so in ways that drive forward innovation, that build on and further help to further advance, indeed, the very climate science that will help us navigate these challenges? This IPCC report was, in my view, a call for radical action on water. It couldn't, we talk about code red for humanity, it couldn't be a deeper red for water and water management. And so as we therefore go forward into the coming set of sessions over the many coming days in the COP at the Water Pavilion, we need to focus on three critical things. One is, what's the policies that we need? In the water community, we're very used to talking about that. What's the policies that we need in water governance, in climate, across sectors that can help us manage these risks? How do we mobilize finance into the right places, into the right measures for both mitigation and adaptation? And how do we promote and accelerate the right kinds of action across governance, climate services, through to infrastructure and water technologies? We have to recognize that water security is therefore at the heart of climate action and climate adaptation. It's codependent with climate security, it's codependent with food security, and we need to move those agendas forward together. A weakness in one is a weakness in all, and I very much look forward to the program of events coming up in the Water Pavilion, which will help us to make those connections well and make those connections well with how we move forward on water security in the face of the climate changes that were presented today and the climate extremes and extreme events that we're going to be coping with in the years and decades ahead. Thank you, Aditi, and back to you.
Thanks, Mark. Thanks, everybody, all the speakers and the panelists. So with this, we come to the conclusion of our event, which was live streamed on YouTube, which I believe quite a lot of people watching it. Yeah, thank you, everyone. And let's keep, in our own ways, strive towards that 1.5 degree goal. And let's keep water at the center of climate change. Thank you.
Thank you, Aditi, for organizing this important session.
Yes.
Thank you. Thank you all.
Thank you. My pleasure.